So we have done the Newton's law of collision, correct? Newton's law of collision is done, right? As a gentle reminder to the law, if we have two masses, and if the first is moving with speed u and second is u2, let's say, and we are assuming this to be one-dimensional collision or collision. So for the collision to occur, the first situation is very obvious that for collision to occur, u1 must be more than u2. But once the collision happens, the velocity of the first particle cannot be greater than the velocity of the second particle if they are in the same direction. And after the collision, if I say this is the situation just before the collision and this is the situation just after, then after collision V2 will be more than V1. In the worst case, it can be equal, which is called the perfectly inelastic collision. But in general, it is always more than or equals to V1. So the coefficient of restitution, as we know, is defined as the relative velocity of upon the relative velocity of approach. Now, the word approach and separation itself is a relative term, but still, just to emphasize that we have to find the relative velocity, and we should treat each object as one surface. So you can arbitrarily assume that this is some surface, and see the surface which will hit each other. So the whole idea is that at what rate these two surfaces are coming closer to each other or separating away from each other. So the whole idea is take this ratio and call it coefficient of restitution. So velocity of separation will be equals to V2 minus V1. And in the worst case scenario, it can be 0 because if V2 and V1 are equal, then this is 0. It means they will not separate at all. And the approach will be equals to 1 minus 2 because 1 has to be more than 2 to get this answer. But it is also not necessary that every time you will see this situation that everything is moving in the same direction. So in many cases, you will come across that they are moving in the opposite direction. But the definition remains the same. Okay. So let's say we have two bodies which are again identical bodies. Let's draw the situation first. And if I draw the so it is quite possible that these two before and after may have a velocity like this. And after hitting, they may go like this. This is quite possible. You may call this as U1 and U2, and then you may call this as V1 and V2. So U1, U2, V1, V2 are magnitudes. And this is again a case which is just before collision to just after. And so the definition of E will be the relative velocity of separation. Now, at what rate they will separate? If you look at this situation, then this is definitely the sum of them. And the relative velocity of approach is also the sum of them. So the relative velocity of separation or approach means at what rate they are coming closer. That's interesting. So now in a situation like this, so let's say we have a situation in which one of the body is at rest. This is a body which is not moving. And the other body which may be moving along this direction with some speed u, or let's call it v naught, and this is at rest. So this is the case of oblique collision as we discussed in the last lecture. So when this body will eventually hit this sphere, so we have to think of the instant before it is hitting. So just before the collision, you can take. So right now it is still moving with velocity v naught, and it is about to hit slightly. It is about to hit. Then the velocity of separation or approach as we define it is defined as the rate at which the surfaces come closer to each other. And to understand this relation of approach or separation, we must join the center to center. Why this is so? Because the surface which is going to be hit will be this surface, which I can draw by this yellow line. So this is the point of impact, and this will tell you that this surface and this surface will hit each other. So the rate at which they approach each other, let's call this angle theta. Later on, we can derive this theta easily from this simple diagram. So this is definitely, because this is R, this is capital R, this is capital R. So in a situation like this, the sine theta is also obvious how much will be. So that will be capital R upon R plus R. Now these kind of indirect calculations are very much obvious in the case of oblique collision, which you will face eventually. And now once it will hit, the impact will act this way along this pink line. This is the direction of impact. And this impact will affect the motion of both the masses. So now how we deal with approach and separation in this case when we have oblique collision. So the idea is simple. You just extend this line first. So even in your like solution, when you try to solve the question, you have to think this way. And then again, let me divide this into further two parts. Oh, sorry. So the situation before and after will denote by the center. So we call C1, C2. So don't draw the object, just draw the center. So you can draw two tiny dots here for the sake of illustration, and draw the two dots here on the other side. So let's call this is C1, this is C2, and again C1 and C2 just before. and just after cooling. So now the velocity of the first particle just before we know in this direction and in this direction. So we are trying to resolve the velocity in the two mutually perpendicular directions because we know that this is v naught cos theta and this is v naught sin theta. But the second particle having zero velocity. So now the approach is always determined along the common normal. So we can call this as common normal. Or the other way of thinking is that this component will never help you in bringing them either closer or away. And once the impact will occur, this component, because is at right angle to the impact, this component will remain as such. And because of the impact, the component along this direction will be not different. And the other particle will get the impact this way, so it will only move this way. So to start with the assumption of variable, we can call it as V1n and we can call this as V2n. And the double subscript is actually trying to explain that this is the component taken along the common normal. So here we are not trying to call it a V1, V2, we are trying to call V1 and V2n. But these are the components along the common normal, and the other thing is right angle to the impact. So in case of oblique collision, whenever it comes to the writing of definition of, you must write along the common normal because that is only meaningful. And therefore, you can clearly see the velocity of separation here will be V2n minus V1n because they should go away from each other. And the approach is because of the only one component, which is V naught cos theta. So you need to understand the ways of writing E in different situations. So in different situations, we have different representation about E. So in one dimension we have seen, in two dimensions we have seen, and in two dimensions the only case that we will face in the examination is hitting one object and the other object is coming and one is at rest. So the situation which can be asked in the examination is one is stationary and other is coming and impacting. So it will never be asked that both are moving and then solve the question, because in such scenario we have no idea at what angle one will hit the other because we don't know the future. Okay, so these questions will never be asked, don't worry about it. In one dimension, because the velocity will follow the same line, so such component like this will never occur. So in 1D, the approach and separation we can directly write without worrying about the component because there is no component at all. So only in the oblique collision we have the component, and so we have to write it accordingly. And we have already seen about the collision of two surfaces in which one surface is permanently fixed, like floor, ceiling, wall. So when two objects are hitting each other, in which one is permanently fixed. Now the word permanently fixed we can extend to the case also when out of two body, one body is infinitely heavier than the other body. So in all such cases, the fixed surface will not move, or the very heavy object will not buzz or will not change its velocity. So all the impact will affect the lighter object. So that is what we saw in the last lecture. That if you have a ball and if there is a ball and if it is coming and it's going with V, and if E is the coefficient of restitution, so if I'm calling this as a wall, if this is wall, then definitely the wall velocity will be constant no matter what you hit. So the ball will change. So it may hit and will turn back with some speed, let's call it small v. And we have seen in the last class that E was equals to. So velocity of separation here will be V plus capital V. If I'm assuming this to be left, and the approach was U minus. So of course these things we have discussed in the last lecture itself. So now the question is how to solve the question of one dimension collision. So in every collision, in general, we know that some energy loss may be accompanied along with the momentum transfer. So when two bodies hit each other, let me draw some situation of that. So when two bodies hit each other, they carry some momentum. So we are taking the identical sphere so that the collision is one dimension. So let's say this is U1, this is U2. So we have also seen that in case of maximum deformation, when they are in the worst case scenario, the two will move together and they will move together with velocity v, and this v is basically equals to uc, and then they separate. So there are three stages of collision. One is they collide, they deform, they reform, they separate. So the deformation phase and the reformation phase will start from here to here. So from the moment they hit till they become maximum or maximally deformed, so from the moment you hit and you go to the maximally deformed state, when the velocity of both the mass will be same equals to UCM, is called deformation part, and then this is called recovery part. So in every collision we have two state actually. So for the sake of mathematical simplicity, I am taking all direction to be same so that I need not to worry about the plus minus sign. So now there's some impulse is in action. So when they collide until they get maximally deformed, there is some impulse which is in action. And the impulse which acts during this part, we call it a JD, and the D represents for deformation. And from the maximally deformed state to the state when they are about to separate, the impulse acting is called GR, which means the impulse of recovery or restitution. It's the same thing. So the meaning of what a restitution is recovery. So now we have one alternative definition of E. So E is also defined as the ratio of impulse of recovery upon impulse of deformation. So the impulsive force developed during the impact from the moment it hits till the moment it is maximally deformed. So this JD is having the product of force and the duration, which is definitely very small. So in that case, we call deformation JD, and then the recovery impulse we call JR. And apart from the definition of E, which we just saw, this is the alternative definition. And sometime in the examination, they may ask you the relation. So impulse of recovery is E times impulse of deformation. So now the question is, what is the value of these two? How we can calculate? Okay. So let's derive the value of GR and JD one by one. So keep this diagram in mind because this is what we will use to derive the value of GR and JD. So we'll start with for JR. And as a tool, what we are going to use is called impulse momentum theorem. So you can think this way. The first mass M1 is moving with velocity U1 before the impact, and then suddenly the impact starts acting. That's called GR. And at the end of deforming state, you reach the maximally deformed state. And at that instant, you are moving with velocity V. So how the impulse momentum theorem we can write here? So we can see the what is the momentum of the first object. So first of all, impulse momentum theorem, I hope you remember, is J equals to delta P. Or the other way of thinking is that J equals to the final momentum minus initial momentum. Or the other way of thinking is that initial momentum plus the impact will lead to the. So now I have kept everything in one dimension to keep it simple, not to use the vector sign. We can say initial momentum is m1 u1, and the impulse of recovery is going to support the momentum or oppose the momentum. Tell me, guys. So impulse of recovery will support or oppose?
Oppose.
Now the opposition means it will eat away some momentum away from it. So m1 e1 was the initial momentum, and you have taken away something. So what you're left with? M1.
And wave one.
So we can say JR is M1 into U1 minus V. So I'm particularly writing the GR by M1. This is what I'm interested in. So similarly, if you draw the ABD kind of thing for the second mass between the two state called the maximally deformed state. So the impact on the second mass will be, in a way, it will support, right? So the mass number 2 was actually moving towards the right with velocity u2, and the impact will hit it and will support. So it will velocity will grow from u2 to v. So how we write the impulse momentum theorem in this case? So we had momentum m2 u2. I received one impact, which is like I got some supply of momentum to me, and now this has changed my momentum to a new value m2.
M2V.
Correct. So from here you can see that gr by m2, if you rewrite, will be v minus u. So the third step is adding the 1 and 2 equation. And why we are adding? Because the v is the intermediate value which we don't want. And therefore 1 and 2, if you add, what you get? gr 1 by m1, 1 by m2. And if you add, you can see clearly it's 1 minus 2. So I might have defined something called reduced mass. For any system of particle, the inverse summation of all mass, it could be any number. If you add all masses in inverse, it is equivalent of 1 by mu, and the mu is called reduced mass. And you may be wondering why we call reduced mass, because the value, this is like a parallel combination of a resistor. And we know that when you combine two resistors in parallel, the equivalent resistance will be less than the least value.
Yes.
So now, because we are talking about only two masses, then for our case, the 1 by m1 plus 1 by m2, we call the reduced mass, and this will give you the answer mu equals to product upon summation. Now you can take any number. Let's take number 5 and 4 and write the product and summation. The answer will be 20 by 9, which is roughly 2 point something, right? Which is less than any value. You can see the equivalent answer is always smaller than the any individual mass. That's why the name is called reduced mass. There is no particular reason for this. So reduced means the effective value is less than any individual value. Yeah, so this is called mu. Of course, this is mu. So now what we can realize that the value of JR is mu times u1 minus u2. And if you remember, the 1 minus 2 was the velocity of approach. This is the u relative. I mean, let me just write down u relative. So now the formula we have received, gr equals to mu times, let's keep it, this is a numerical value, and this value is also important. Now this was the analysis which we made for the deformation duration, like from the moment you collide till you get maximally deformed. So we have, oh, I made a mistake here, a big mistake, sorry. No, I should have just changed a D, all mistakes. So in my mind it was D, but I was writing R. You just have to change all to be JD. And the GI is the recovery phase. So in the recovery phase, you can see that you go from maximally deformed to the separation. And the impulse will keep on acting in the same way, even further. So for JR, the first object M1 is now in the state V, and impulse is still acting backward for the first mass JR, and now eventually it will move with velocity V1. Now you can also realize something, that during collision, the body goes from their individual velocity to one common velocity, and that is called the velocity at maximally deformed state. And that common velocity is very famous, that is equals to the velocity of center mass. So you may be asked in the examination, what is this V? So this answer is very important. So the common velocity which they attain in their lifetime in any collision for a two particle system. So there will be one moment when both will move with together in with same velocity, and we call it V equals to UC. And why it is UCM? Because of course UCM is constant. So now if you talk about the GR, so from the maximally deformed state till the state you separate, the GR will further eat away your momentum. M1V is not where it will stop, it will take away some more momentum. And now you will move with M1V1. So the GR will be equal to how much? M1 V minus V1. So again, GR by M1 will be equal to. So what about the M2? M2 from the maximally deformed state goes to the V2 state. And in the process, it gets the support of the JR again. And therefore, sorry. So the way of writing the impulse momentum will be M2V. And you can see the impulse is taking it further ahead. So V2 is bound to be more than V1, as you can also realize. Because V1 is going below V value and V2 is going above the V value. So V2 is more than V1. That's why they separate. So the GR equals to how much? Okay, I'm writing directly. It's V2 minus V. And the next step, which is the obvious step, is adding 1 and 2. And the moment you add 1 and 2, you can see GR1 by M1 will be V2 minus V1, which simply means GR equals to mu times So now we can go back to the definition. So now the definition of E, which is the actual definition, is impulse of recovery upon impulse of deformation. And this must be equal to mu times V2 minus V1 upon mu times. And now you can see this will lead to the same formula as we defined by the Newton's law of collision. So why the mu gets cancelled out, right? So now we have many formulas to deal with. So the JR depends on the separation part, and JD depends on the approach. So just remember this formula because this will be handy in solving some of the numericals in which they will ask you. So the impulse of the impulse for the entire process, that net impulse is the sum of these two impulses. So we have just bifurcated the impulse into two categories. One from the moment you hit till the moment you are maximally deformed, and calling this as impulse of deformation. And the beyond that we are calling as an impulse of recovery. If someone is asking you what is the total impulse. So the net impulse will be how much? What do you think? What is the total impulse? Tell me guys. So if I add these two equations, what we should get?
Nu multiplied by V2 minus C2 plus C1 minus V1.
Okay, so let's not add this. That's the bad thing. So the idea is the impulse is definitely internal. Okay. So
Zero.
if you think of the net impulse acting on a system, so if you're taking M1, M2 as a system, then these are internal force. It must be zero because momentum is not zero. So the net impulse, if we talk about the system, so we are writing JD and JR for individual, but for system there is no impulse. It is internally governed process. And basically, if you try to understand the role of JD and GR, they help in transferring the momentum between the objects like M1 and M2. So it is the JD or GR which develops for a very momentarily small duration, and in that duration they are capable of exchanging the momentum and so the velocity. Okay. So in a collision process, it is a J, that is the impulse, which helps in exchange of momentum. That's it. So now the obvious question is how we solve the question of collision. So we'll take the case of 1D collision, how to solve one dimension collision. So it may be block something. So the number of variables which we can have is 1, 2, 3, 4, 5. You can see these are 5 variables. So now, of course, we cannot solve 5 variables. So because if you want 5 variables, then you have to give 5 equations. So in general, if you look at the problem, or you can say problem statement, they generally give E, and out of these 4 variables, tactically they will give you either the two. So now, in a very easy problem, they give these two and they will ask these two. But in some better problem, what they do is they give a mixture of any of the two. So they may give these two or these two or these two or these two, and they may ask the remaining two. So essentially, the number of variables that we have to deal here will always remain two. And why this so? Because the number of equations that you can encounter will be only two. Okay. So now these are problems which involve the E. But you will also come across a situation and the E is not given. So if E is not given, it does not mean that they will give you some more equations. So they will still give you either of the two. And or you can say you can take any combination. So the moment you see the absence of E, you must realize the fact that it cannot be solved. So you must look for some energy relation. So if this is the case, look for energy relation. So if you read carefully, you will realize that either directly or indirectly, they must have revealed what kind of energy relation is this? So they may say that a kinetic energy final is more than, less than, or equals to, or a scaled version of initial. So either of the information will be given to you that at some part, I mean, the kinetic energy is some fraction of initial. It may be more than one also. So the final kinetic energy may be 1.5 times the initial. Maybe it is less than fraction equal. So any combination they will mention. So to deal with such question is that you have to write the momentum conservation and energy relation. And that is obvious because when they don't give E, they give the energy relation. And the first category of problem you can, if you read, it's very obvious. So they will give you E and the two velocity out of the four. So as a student, what is the biggest challenge? So as a student, what I have seen that they struggle to assume the value. So you may be wondering that how to assume the variables. So if I tell you the situation, let's say this is U1, this is U2. Now after collision, something will occur. So as a situation, I am telling you that let's say U1, U2 is given. And they will never talk about V1, V2. This is what you have to assume. So it's very obvious that you must assume the way you want it, no matter how you assume. So make some logical choice. And even if you make some wrong choice of V1, V2 in terms of direction, I'm saying, it will never affect the answer. But the way you choose V1, V2 as an direction, the definition of E, that is the coefficient of restitution, will alter. So let's, for the sake of analysis, let's make it this assumption that after collision, so I'm saying this, after collision, let's say the block, red block bounces back. Quite possible, not a big deal. So now the the assumption of V1, we should keep left, not a big issue. And then the steps that we have to follow. So we are assuming these two as my system. And if we choose these two as system, then definitely the impulse developed will be internal, which means the momentum will be conserved. The first step of solving any question is conservation of linear momentum. Now, because it's one dimension, so you can choose either direction as positive or other as negative. So let's take the right as positive and the left as negative. And write the momentum as per the sign convention, because it's momentum which is a vector quantity. You cannot just add the numerical value, because many times students feel that okay, it's a number, let's add them. So conjunction does not mean you're adding numerically, you're adding vectorly. And because it is one dimension, so we are ignoring the sign. So one dimension is not a scalar equation, it is still a vector equation. And the directional sense should be respected. So if you take a right as positive, you must take a left as negative, or vice versa. So you may begin with any of your choice, but you must write things accordingly. So let me write the conventional part. So we can add M1, U1. The first mass will have momentum towards right, second will have right. So I'm adding both. Now this is the end of my initial momentum. And it must be equal to final, which is minus M1 V1. Why? Because it's going left. But M2 V2 going right. And now I call it question 1. I cannot solve any question like this unless you don't give me the E value or the energy relation. These are the two crucial things to search for. So sometimes they call the collision to be perfectly elastic or simply elastic. So the moment you read a question and they say collision is elastic, but they don't give you E. So they call collision as elastic, but they don't mention E value. Now this is some subtle hint to
E is
student.
equal to 1.
Correct. So it means you have to take E equals to the or choose this as perfectly elastically. So now these are like some tactical things which we need to remember, although it is implicit in all problem. But when they say elastic and they don't give E, it's one. But if it is elastic and if you mention E, then you know what to do. Now, if the collision is perfectly inelastic, then E is 0. So inelastic, so perfectly inelastic or inelastic, and they don't mention the E again. So if you know that it is perfectly inelastic and they don't mention the value of E again, then you must take E equals to 0. Now these are some implicit assumptions which we have to make while solving the numerator. So the definition of E will be very simple. It's a separation upon approach. So just look at the value, the arrows and think of how to write separation. So here the separation is obvious 2 plus 1, but the approach is 1 minus 2. And the E is a positive number, so you must write the positive value. So you must think of that how to write the values. That's it. So don't worry about the direction. You write what is the separation and what is the approach. So here the separation is V1 plus V2 because they will go away from each other. And the approach is definitely 1 minus 2 because 1 should be more than 2 to hit. Okay. Now I'm not going to solve this question, but this is the way you have to start with, and then of course you have to proceed further to simplify this, and that will lead to the answer 1 and 2, V1 and V2. So every one dimensional collision you must solve this way. Now the question is how to solve the two dimensional collision. So probably we have the situation here and I can solve here only. So in two dimension, which is to the oblique collision, the definition of E is obvious. The next step is only conservation of linear momentum. So the conservation of linear momentum says that the momentum is conserved. So the rule in two dimension is you simply conserve the momentum along the line of impact. This is the line of impact also. So common normal is the line of impact. So the way of writing is M1, let's call it M1. But the velocity of the first particle along the line of impact is V naught cos theta. It's not V naught. So we don't write M1 V naught. We write M1 V naught cos theta. Because whatever be the collision, this will remain fixed, no? So the second is 0 because it was at rest. And after collision, it will be M1 V1N plus M2 V2N because I'm taking both as same direction. So we equation 1 and equation 2, and then you're done. So we're done with the two-dimensional collision. This is how we proceed. Again, I'm not solving the question. So although I have not solved the question completely, but there are some situation which we should remember as a final result. So we'll take the case of perfectly elastic collision of two equal masses. Now, this is a case which we all must remember. So what exactly happens if we have a collision of equal masses? We have two blocks, but they have same mass. Before U1, U2. So now because E equals to 1, so again, still you write the definition of E only, but you can substitute 1 equals to separation upon approach. So basically, if the collision is perfectly elastic, then separation rate will be always same as the approach rate. And if you write the momentum conservation, things will be pretty easy for you because you can just take M common, which means the 1 plus 2, obviously 2 plus 1 equals 2. And now solving these two questions are very easy. So we can say from 1 and 2, V2 minus V1 is the difference, and V2 plus V1 is the summation. If you just add, what we get is 2V2 equals to 2U1. And that's very nice answer. V2 is U1, and so the V1 will be U. So how we present this interesting result? So when they will hit it, the V1 itself is the U2 and V2 is the U1, which means they simply exchange the velocity. So in the perfectly elastic collision of equal masses, the velocity of colliding bodies gets exchanged. So the first acquires the velocity of second and second acquires the velocity of the first. And that is very interesting result. So you can mention as a note here. In this case, velocity gets exchanged. That's it. So you may think this way, like if these are two masses of E1 and E2, which one is bigger here? One is more than two. And because one is more than two, so who will go, when who will hit the body is two, so U1 is going to hit the, you can see U2. That. And after hitting, you can imagine that it will just penetrate through this and will go ahead. It is like eventually U1 will lead and U2 will lag. And they are like some ghosts, they can go through each other. You can think this way also. So if I just draw identical mass with same color, and if I call this as U1, if I call this as U2, and this is nothing, and if I know that every E is 1, so at the end of this entire collision, I can tell you the exact answer of the last mass. So let's call it 3. So when 1 and 2 will hit it, so because 1 is this, so now the first mass will move with U2, and the second will move with U1. This is the first step. And when these two will collide, the U2 This will become at rest, and the 3 will move. So at the end of the collision, we can know exactly what will be the velocity of masses. So let's say we have a Newton's cradle, which is a very famous example of the same. One, two, three, four. Let's say this is the mass which is moving with velocity v0. All are identical, not only in mass, also in the shape. And now all collision is perfectly elastic. Let's put some number in one. Sorry, one, two, three, four, five, six. So the moment one will hit the two, what will happen? One will come to rest because the two is at rest, and the two will try to move next with velocity v naught, but it will hit the three. So again, it will extend the velocity, and so on, so on, so on. Eventually, what will happen? After the collision, the situation will be like this. So what will be the situation? One, two, three, four. One is here. One, two, three, four. And then the one which will walk away is six. Because the exchange will take place in no time, so they will come to rest immediately. So the first particle will come to rest, second will move, second will come to rest, third will move, third will come to rest, fourth will move, fourth will come to rest, fifth will move, and the fifth will come to rest, and only six will move. Eventually, it will go with zero. Now, even if I put 1,000 or 1 lakh or 1 million such identical balls, the moment you hit the first, only the last will go away. Understood? So the one will hit the first, I mean, the one will hit the two, and eventually what you will end up seeing is that six is moving. Now, these things you must have seen often in the carom, in a game of carom, because if you have a multiple vines and if you hit it, the stacker hit the first and only this will go away, rest will remain intact. So what is happening in such situation is basically the event of perfectly elastic collision. So in variety of problem when you deal with, this part is something which you need to solve. You just remember the answer and from there you solve. If we have identical mass, then the velocity will be exchanged. So let's take one simple example which you will see in text as our numericals. So we have two mass. Change the color. M, M, 2. So that the spring is initially in the unstretched condition. The question is find the maximum compression in the string after the first block hits the second block. So find maximum compression in the spring. The first part is collision between the 1 and 2. And although the spring is attached to the first mass, but there is no spring force, because spring force demands deformation. So when 1 and 2 will impact, it is as good as there is no spring. And even though there is a spring, it will not matter, because the spring is always the non-impulsive force. We know that spring force is the non-impulsive. It never impacts the value in a short duration. So it may have the long-term effect, but there is no short-term effect. So you should not be worried about the conserving the momentum just because the spring is attached. You should not worry. You can conserve, because we can conserve before and after. Even the spring force is present, we again can conserve before and after. So the colliding bodies is M and this 1 and 2, let's call it 1 and 2. The first step is obvious. Simply exchange the velocities. So 1 will come to rest and 2 will move. So basically this problem is equivalent of this problem. So it is just a way to extend the problem, but this is very much same as having two blocks of mass 2m and m, and the block, this is given a velocity v naught. So either I can do this drama or tantrum to create the same situation, or you simply say that this is the v naught. Okay. So once we have this v naught, then we know how to find the maximum compression. So what is the maximum compression? I hope you remember this situation.
Yes.
So at maximum compression, what happens? They move with same velocity,
Velocities are same.
and it will be towards the right. So we can say at maximum compression, so you know mv naught equals to 3mv, which means v equals to v naught by 3. And then you write the energy conservation, which means half m v naught square equals to half 3m v square plus half k x max square, and this is how we solve. And after solving, you will get the answer as, if you remember, I gave you the shortcut, under root of reduced mass by k into u relative.
Yes.
So the reduced mass is how much? It's 2m by 3. After solving, you can get direct answers. So for competition, you can just choose this formula directly. That's not a big issue. So in fact, this entire question we can solve in one line, because we know the answer. It's we know this will be v naught, and then we know the formula like this. So you can just solve in one line. Okay. So I hope you have done the enough practice in the practice sessions, tutorial session. So we'll go to something new. So our next concept is very powerful concept, which will simplify all calculation. And in many situations, all the challenging problem we can solve mostly in 6 to 10 seconds. So even the question from Eroda we can solve in 5 to 6 seconds. So our next topic is called center of mass as a frame of reference. And our discussion will be confined to the two particle system. So imagine we have two particles. So let's say the mass is m and this mass is 2m. So if it simply means if I divide this into 3 equal parts, then the center mass will be here, right?
Yes.
So now let's say both are moving towards each other. So after some time, let's say the first comes here, second comes here, then they come even closer. In fact, let's say they collide now. So the whole idea is whenever they will collide, where is the center mass now? Because they are like particles, so I can say this is the center mass. So center mass was here, now it is here, and now it is here. Because if every mass is at the same location, then we can say that is the center mass. So now imagine a guy, an observer sitting at center mass. So for him, or for the observer, the collision will always take place at center mass, isn't it? For the obvious reason. So whenever two particles will collide, center mass will be there only because both are there. So if every particle is located at the same location, then center mass will be at the same location. So in the CM frame, both will collide at center mass. Now, does it depend on the fact whether the particles are moving in the opposite direction or same direction? So now, will they collide at center mass or somewhere else? Tell me. Where these two will collide? At which location?
Sir, at center of
Yeah. So no matter how they move, if something collides, it collides at center mass. Because if every colliding object is at the same location present, they see the center mass. So from here, what we can infer, what we can say that in CM frame, if you are sitting there and if you have just two particles, no matter how they are moving, they can only move either towards the center mass or away from it. There is no third way of moving. So in CM frame, whether you move in one dimension or obliquely, in CM frame, the two particles either move towards the center mass or recede away. So there is no third movement. Okay. So let's prove it mathematically. And at every step you can raise your query because this is very crucial to learn. And this will let you master this chapter in a way which you have never felt before. So we'll keep the analysis simple. So let's say we have two particles. Let's say they're moving in the same direction. So we know from the definition if this is U1 vector, it's called vector in general. So what is the velocity of center mass? So this won't be difficult to calculate.
1 upon m1 m.
So you know the velocity of center mass because you know individual velocity, so you definitely know the velocity of center mass. So now the first step is what will be the velocity of the first particle with respect to center mass or cm frame. So we denote by u1c and we call it velocity of first particle with respect to center mass. And by definition, we know u1c basically refers to 1 minus c or cm. So that is by definition of a relative velocity. And as I am doing this calculation, you also do the calculation. Then only you can, kind of realize. So everyone out there, please do write the way I'm at. So we can write u1 minus ucm, which is m1, u1, m2, u2. So u1c we can write as m1 u1. I'm taking LCM now. m2 u1 minus m1 u1 minus m2 whole upon, and something very interesting happens. So it is 2 minus 1 minus 2, which is again something like approach, right? Now the next part I will not solve, I can directly write. So similarly, u2c, just interchange the 1 with 2 and that's it. 1, 2, 1, and then it really doesn't matter if you interchange or not. So now we know the velocity of each particle in the CM frame. And if you're doing along with me, then I hope you must have got the same answer, correct? So are you getting the same answer? Yes or no?
Yes, just solving some last step. Yes, sir.
Okay. So the next step is, can you find the momentum of each particle in the CM frame? What is the P1C? That is the momentum of each particle in the CM frame. How much we have? M1 into U1C. And if you do so, you get M1, M2. So P1C is equals to mu times because this is reduced mass, which is very famous. So we can convert this into reduced mass, and then we have this answer. And similarly, if you write the P2C, again you can realize something interesting. And now the only difference that you can realize that the momentum, that they are exactly the same numerically, but they are exactly opposite in direction. Exactly opposite. And that's why I said that the direction of momentum of the two particles in the CM frame will be always equal and opposite. So before collision, they approach towards center mass, and after collision, they recede away from center mass. So in the CM frame, it looks like they're coming closer, and then they hit, they go away. So the difference between the P1C and P2C is only direction, not the magnitude. So we can say that so if you add P1C with P2C, it turns out to be 0. And this is not something unusual. We have seen this in the very beginning, in the very first lecture, that the sum of momenta in a CM frame is always 0. It means center mass is a frame in which if you add all momentum of each particle, it will end up giving you 0 answer. And why it is so? Because the VCM formula, if you again recall, is M1 V1 plus M2 V2 and so on. In a CM frame, if you write the same answer, MVCM, in the CM frame, you will write M1, and this is the VCM VCC, M1 V1C plus M2 V2C. And we know the velocity of center mass in the CM frame itself is how much? 0. Because the center mass, if you are sitting at center mass and if you are asking what is the velocity of center mass in the CM frame itself, it must be 0. It must be at rest. Which simply means that if you have any number of particles, then if you add their momentum in the CM frame, it will always turn out to be 0. So this is what we discussed in the very beginning. Now, for two particles, we have just proved again. So P1C plus P2C is 0, and therefore P1C is minus P2C. If I take mod both sides, I can say that numerically they are equal. And because they are numerically equal, then we must have some nice notation to deal with. We call it P mu. So everything in the CM frame becomes P mu. And the formula is also not very difficult to remember. It's mu times U relative. The U relative is the initial momentum in the CM frame. And then after some time, if we have V1, V2, then we use V relative. So in general, if you know the velocity in the ground frame, you can find the momentum of each particle in the CM frame directly by the formula mu times U relative. And once you know the momentum of each particle, then the next step is further very easy. What is the energy of the system in the CM frame? Okay. Let's try to calculate the energy of the system in the CM frame. So calculation of kinetic energy of system. So what we know that from the conservation of linear momentum, we know that when you create a system, you impart some velocity to any particle of the system or all particles of the system. The center mass starts moving. And once the center mass will be set into motion, that velocity will never change. Why? Because center mass velocity can only be changed by the external agency, So internal collision of particle will never change the velocity of center mass. So in a way, you can say that the kinetic energy which is carried by the center mass will remain with the center mass. So think this way, that let's say we have a system with two particles. And they may have some velocity in random direction. So the center mass will also have some velocity. So let's say this is the center mass in general, and it's going something like this with u. Now, no matter what happens to the body, this center mass will always be in this line, no matter what happens. So once you know the initial direction of center mass, it will remain forever the same direction and numerically also. So value wise or direction wise, it will remain same. Okay. So now the question is, in the CM frame, what happens? What we see in the CM frame? So there are two ways of thinking. So first of all, if I ask you what is the total energy which is given to the system, how much energy we imparted? The answer is half m1 u1 square, half m2 u2 square. Now this is the actual energy in the ground frame, okay? But we also know that by default, the moment we give u1, u2, there is a sudden rise of UCM. In a way, you can say center mass naturally acquires some velocity and so the energy. So what is the energy acquired or kept by the center mass? I can say m1 plus m2, the net mass of system, and UCM square. Now you have no control over this energy. Now this is something very interesting. So we cannot affect this energy. So although we have given energy to the system of this magnitude, but this value on the right, this you cannot take away. So this is the energy which is carried by the center mass. So the one way of thinking is that the moment we impart energy to a system, this is the energy which goes to the center mass, which is like a tax paid by the every employee of a company. So this is the your net earning, but you pay this much tax to the government of India. And the difference of the two will be the energy which we call energy available in the center mass frame. Why? Because if you are sitting on center mass, if someone is sitting here, then he will see center mass at rest. But at the same time, he will not see U1, U2, he will see U1C, U2C. So when he will calculate the energy in the CM frame, then that energy is something that he can utilize for other purpose. So your income minus tax is your net take home salary. And this energy you can use for purpose of your choice. So the core idea is that whenever we create a system with some energy, a part of that energy goes to center mass without saying. And the remaining energy is something which we can use for other purpose. So we can convert into other form of energy if we need. And in fact, the loss in kinetic energy by virtue of collision always happens as a fraction of that left out energy. So let's say you have given 100 joule, and let's say the 60 joule is taken by the center mass. So the 40 joule is energy available, and then a part of 40 can be spent. So you may spend this energy in some other purpose. So no matter we incur some loss in the collision process, the loss will not affect this part, and therefore the UCM is maintained, and so the momentum is conserved. So sometimes it happens to the like us that intuitively we feel that if energy is lost, then why not the momentum is lost? The answer is the momentum is carrying only a fraction of energy, not all energy. So you cannot lose energy more than the difference. So you cannot lose energy in the process of collision more than 40 joules. This is the maximally or maximal available energy which can be lost. So if you want to lose more than that, it means some external force will come into picture and will snatch away the energy or will slow down the center of mass. So in the absence of external force, the difference we can snatch. Another question is how to find the difference. So the best way to find the difference is just go in the CM frame and calculate the energy. Whatever you will see is the difference. So this energy, the difference is having a name in physics we call cumulative kinetic energy. So when you read the book of IE Erodov, they use the word cumulative kinetic energy, which means the energy available in the CM frame. So in fact, I should mention this as a note. So what is cumulative kinetic energy? It is the energy of system. So when you impart energy to a system, then a part goes as a tax or as a bribe or as a whatever you think of. And the difference is something which we use, which we call cumulative. And the better way of thinking, calling this energy is called the free energy. So this is the energy available in a system which can be utilized for other purpose. Okay. So let's try to calculate this value, and it's very easy. So we say the formula is Ke mu for cumulative, because anything in the CM frame, the subscript becomes mu. That's it. And because energy we can write by formula of momentum. So we know kinetic energy is P square by 2m. So for the first particle, I can say P1 C square by 2m, and for the second particle, we can write as 2m2. And it is actually P mu square by 2 1 by m1 plus 1 by m2, which is essentially the P mu square by 2 mu. That's the only difference of rank. And that's very easy to write because we know the reduced mass, we know the momentum in the CM frame, and we can add the. So the cumulative energy is very simple formula, P mu square by 2 mu. So the mass is replaced by reduced mass, and this is the how we convert the answer in the CM frame. Technically, it's very easy to remember. Just you replace the P by P mu and M by mu, and then you're done. And the other way of writing this could be, so if you remember the P mu, it was mu into U relative square by 2 mu. So this becomes half mu U relative whole square. And then now this is again simple. So it's half mv square, the v is replaced by U relative whole square. Now it need not to be U only, U relative. I'm saying this is the velocity relative, v relative. So in general, if we have two particles with velocity v1, v2, so whatever is the v relative, the kinetic energy at that instant in the CM frame will be simply half mu into v relative magnitude square. That's it. So if you know the velocity, this is the answer. Now the only time when this will be zero is when the v relative is zero. So whenever you have a situation when both will have exactly same velocity. So if you are solving a problem and you know that at a given instant both have same velocity, in that case the v relative becomes zero, and therefore in the CM frame you won't have any one at that instant. And why this is so? So whenever a system of particle will move together, this itself will be equals to UC. So in the CM frame, because center mass is moving with UCM, you also move with UCM, which simply means you are at rest in the CM frame. And because you are at rest in the CM frame, the kinetic energy at that instant in the CM frame becomes zero. So now this is the idea behind all calculation which we have done so far. So let me show you some calculation. So remember the problem of the maximum compression in a spring problem, if you remember. Okay. So just to keep it in general, maybe I can use. So let's say we have two masses M1 and M2 attached to a spring, and you give velocity to some mass, only M2. So now, what is the now initially the spring is unstretched. Tell me, guys, in the CM frame, what is the kinetic energy as of now? So K mu initially is how much? So we know the answer is half mu, and the initial velocity relative value, which is v not only, because one is at rest, is square. Now, if I make the M2 as V2 and M1 as V1, and let's say both going towards each other, so depending on which one is bigger, it may elongate or it may compress. But I'm saying that the V relative I can write is 1 minus 2 or 2 minus 1 more square. Or if I say that V2, V1 is backward and V1 is towards right, so I will just add because I'm writing the V relative. So to keep it a general form, I will assume something like this. So in the beginning, let's say this is going with U1, this is going with U2. So what is the kinetic energy of system in the CM frame? What is Ke mu? So the answer is half the reduced mass into U relative whole square. That's it. Now we know the answer for the maximum compression state or maximum elongation. So whenever the system will be in the either maximum compression or elongation, which I don't know. Let's take maximum elongation. So whenever this is happening that they are in the maximum deformation state, they must have same velocity. Now, even if I don't know what is the velocity, I can say they must have same. This is the max value or max compression or max elongation. And now I can see the V relative is zero, which simply means in the CM frame, they have been brought to rest. So now, how we argue? What is the statement? So in the very beginning, you had this much energy in the CM frame, and now you have zero. So where this energy has gone? You may argue, you may ask this question. Now, because there is no loss, because as you can see, it is evident from the discussion that there is no loss. So it must have gone somewhere, and somewhere is nothing but the potential energy of spring. So therefore, I can say the Ke mu must be equals to U spring, because energy is not lost, so it must be somewhere. So the somewhere we can say it must be in the spring. There is no other way out. And therefore, the only formula which we need to write to solve this question is half K x max square, which will simply give you the formula or the answer mu by K into U relative, and you're done. Understood? So how much time it will take to solve this question? Almost no time. So your answer for this question is m1 m2 by m1 plus m2 into K into mod of 1 minus 2. I don't know which one is bigger, and I'm done. So next time you see a problem in examination, and I hope you must have seen questions like this, which are very common in the textbook. So find x max, the maximum motion. Now the two approaches: write the momentum condition, energy condition, and then solve, or write the answer. So it's 2m by 3k, so that's the reduced mass by k, and the u relative is given. That's answer. So how much time it has taken to solve? I don't think more than 6 seconds. In fact, you can do it in 3 seconds. So now let's do some more problems. So if I give one more velocity here, v naught, then the answer will be 2 v naught. And if I make it 2 v naught, this will become 3 v naught. Or if I remove this and if I say this is v naught, this is 2 v naught, the answer is v naught. Understood? So now, no matter which question I give you from the questions like this, you know how to approach. Okay. So let's recall the question that we solved earlier. The wedge and the plank. If you remember, this was the wedge, and we projected a block along the surface. And the question was how much high it can go. At the maximum height of this journey, the y component will be 0, but the x component will be same for both. And now again the same question. At a maximum height, what is the kinetic energy of the system finally? So because the v relative is 0, this must be 0. But what is the kinetic energy of the system initially in the CM frame? It must be half mu v naught square, because that's the u relative, because initially the wedge was at rest and block was moving. So now because the kinetic energy in the CM frame has suddenly become 0 and initially it was having some value, so again you may argue where this energy has gone. So I can say this energy must be equal to the potential energy of block. So the potential energy attained by the block or the system is because of the energy available in the CM frame. because center mass will not give its energy. So whatever was available in that frame, that will lead to the maximum height, and then my answer is done. I'm done with the answer. And now you can solve half m capital M plus m, and this was the h max. So now if you remember that we used to solve this question by the energy consumption and the momentum conservation, and now we are solving it by just one line. So understanding the idea that energy available to us in one frame, in the same frame, and the sudden loss of it, we can always infer what will happen. And let's see the most difficult question that we solve. So the question that I asked was, if we have a plan and there is a block, and if you project the block on a plan with some initial velocity v naught, and there is no friction here, but there is of course friction here, mu. So eventually, what will happen is, so the two systems eventually will move together, and the block will be at a relative rest by displacing some value. So I hope you remember this problem.
Yes.
And the question was, what is this value? What is this x relative? Now I can say directly one. So because the kinetic energy in the CM frame that was initially available was definitely half mu v naught square, because that's the relative velocity, because the Planck is exist. And here the kinetic energy of in the CM frame is 0. So the energy must have been lost by the friction, which we don't realize. And we know that the frictional loss is equals to Fk into x relative. That's it. If you know the work any power chapter, or if you don't know, you can just remember this. And then we are done. So I know the answer is half m by m plus m into v naught square. And the friction force will be, because this is m mass, so this friction will be mu into n, which is mu mg. So I'm directly adding mu mg x relative. See, I can solve in one line. So I know the answer. X relative is by 2 mu g. Done. So any question which you have solved before, if you try to attempt in the CM frame, it will be like a hardly 10-second question. And it saves enormous time. But in a very new situation, in order to apply this idea that requires one different skill, but at least the examples which I have shown you, that you can always apply. So that will save your time in solving a variety of problems. In a new situation, you have to think more about this, that can we use the CM frame and then just reduce this question to one line problem. So even in the Olympiad examination, the questions are very difficult if you solve by the rigorous method. But the CM frame is a mathematical way of simplifying the calculation to an extent which you cannot imagine. So let's do something more about this. In fact, our next lecture will be only based on the CM frame. So we have to deal the entire physics in the CM. So let's take for the collision in CM frame. So imagine we have two objects or two balls you can take. and both are moving with some velocity. So now we know that if you say u1, u2 are the velocity of the each mass, then definitely the center mass will also move with some velocity. Let's the big line, the green, the red line, I'm calling this as center mass. Now this will never stop. So center mass, once you know it's moving forever. So now this is the situation in the ground frame. So we have u1, we have u2, and we have center mass. In the CM frame, we know that if you compare the u1, UCM, u2, what we can say that the UCM must be more than u2. Why? Because eventually both will hit the center mass. So both will hit, which means both will come towards center mass, and that is only possible when u1 is more than UCM. So what is the condition of hitting? One should be more than CM, and this should be more than u2. Then one will move towards UCM and two will move towards UCM. Why? Because this is bigger than u2, so it will go left in the CM frame. So I hope you realize this fact. So this is the ground frame. So in the CM frame, the first particle will move towards the center mass, the wall. The wall will be like a fixed object. So in this case, the wall is not moving. This is fixed. And then one will appear to be moving towards the wall with speed 1 minus UC. And the second particle will be appearing to be moving left. With what speed? Tell me. The speed will be UC minus U2. The value is UC minus U2 because UC is more than U2. And now the wall is like a fixed wall. It's a fixed thing, it will not change. And then we can say the coefficient of restitution is E. Of course, we say this. So continuing with the frame, the CM frame, because the wall is like a fixed, so once you hit it, you will reflect back, and the velocity will be simply E times the approach. So velocity of separation is E times the velocity of approach. If you know that center mass is like fixed body, it's not going to hit, tilt right to left. And this is the CM frame discussion. So I'm saying that in the CM frame, as you will hit the wall, you will just reflect back with speed E times the approach value. But as the discussion has ended, we are interested in getting the answer in the ground frame again. So I want the answer in the ground frame. So it's very simple. We know the center mass is going right, and you're trying to go left in the CM frame. So velocity in the ground frame will be UCM right minus E times 1 minus UCM left. And similarly, the second particle velocity in the ground frame, which I'm calling as V2. So the center mass is going right, and the particle is also going right with the center mass. So net will be UCM plus E times UCM minus U. So now what we are interested in is simplifying the 1 and 2. And if you simplify, we get something very interesting. And now you know the answer that when you apply the conservation of momentum and the definition of E, so if you would have solved in the ground frame, the answer was m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2, and then you write the definition of v, which is separation upon approach. And if you solve these two equations, you will end up getting v1 and v2. So you get something v1 and something v2. So now you have got the answer in a very simplified form, and this is easy to remember, that this entire calculation of momentum conservation and the definition of coefficient of restitution will lead to the answer, which is very easy to remember. It's simply, you can see, up to this term, everything is same, no matter which part you're solving. And the only difference is the initial value. So this won't be difficult to remember, and therefore you can solve all question of collision without conserving momentum or writing the definition of E. Okay. And even there is a more interesting cases. So let me show you some example of how to solve. So let's say you're solving a problem like this, that a block is moving with velocity v naught, mass is m. It hits a stationary block of mass 2m, and the coefficient of restitution is 1 by 2. Find the velocity of each mass. Now that is the question. So after collision, find v1 and v2. Now, of course, if you solve from basic way, you can get the answer. So you write the momentum conservation and the definition of E and then solve. Now here finding UCM is very easy because it is mv naught by 3m. Oh, that's interesting. So we got the UCM in no time. And now I got the answer. V1 equals to 1 plus E UCM minus E, the first particle velocity. Oh, that's done. And the V2 is 1 plus E into UCM minus half into the velocity of fragment, which is 0. So once you are at rest, this is the first part is the answer. So I got the answer as 3 by 2, and this is V naught by 2, this is 0. And this will be 3 by 2 and then see. So it's very easy. So we can get the answer of V and V2 almost in no time. And this will simplify the process. So any problem you're solving in which we have to use the coefficient of restitution or the momentum condition, that we can at least simplify to this extent. Okay, understood? So this is particularly very interesting if one of the particles is at rest. So the one which is at rest, the first term itself is the answer. So because this is at rest, I can tell you the V2 must be equal to simply 1 plus E into UCM. This is the fixed answer. So any particle which is at rest will have this answer, no matter what. Understood? Is this clear, guys?
Yes.
Yes.
So now one typical question which is generally asked is that in every collision some energy is lost, then how much energy is lost? And again, I can get that calculation easily. So we know that that in the CM frame, let's say calculation of kinetic energy due to collision. So calculation of kinetic energy due to collision. So in every collision, we know some kinetic energy lost. So the question is how much it is lost. So the one way of solving is that you find the kinetic energy initial and after, and then take the difference. But that is very bad way. So if you try to solve this with that u1 and then you call it u2 and then you call it v1 and equal to V2, and this is before and after. So what we know that the kinetic energy of system, the very beginning will be half m1 u1 square, half m2 u2 square, then finally will be half m1 v1 square plus half m2 v2 square, and then you will also substitute the v1 equals to 1 plus e ucm minus e1, and v2 equals to 1 plus e ucm minus e. Now imagine if you try to really substitute these values, it will be a very cumbersome process to find the loss. So the loss in kinetic energy we can write as Ke initial minus final, because we are saying the loss. So of course, when you're solving a numerical, you can find the initial value, final value, take the difference. That's okay. But the question is, can we do it smartly? Do we have a better way of doing it? We can solve in one line. So the answer is yes, we can. And the best way to do is in the CM frame. So let's go back to the CM frame. Now, whether energy loss you calculate in the ground frame or CM frame, it's the same thing, because we know that in the center mass frame, whatever was the energy available, if that has decreased, it means energy is lost. Because the center mass will never lose its own energy. So whatever was actually available in the CM frame, only that energy you can lose into other form at max, or maybe a fraction of it. So if you remember that in the CM frame, this was moving with velocity u1c, let's see. So it will bounce back with E times value. Okay. So the momentum of the particle before and the momentum after. So P mu is mu into U relative. So basically the first particle velocity was, now what is P, what is P mu? This is also m1 times u1c. So that's why I'm saying that the value of u1c I can directly find numerically. So if I call it v1c, the velocity after reflection, it must be E mu U relative by m. Okay. So I can say that the momentum, the final momentum, because m1 into, you can also realize from here. So m1 multiplied by v1c, which is the momentum of the particle final momentum, is E time mu into U relative. Basically, I can say it is E times the initial momentum. So this relation always holds true in the CM frame. So even directly at the P final or P mu final is equals to E times P mu initial. Now, if you remember this much only, that's sufficient. So these calculations are also very useful in some other question. If you want to learn, you can write from here, and you can apply for anything else. So I can say that loss in kinetic energy must be equal to the P mu initial square by 2 mu minus P mu final square by 2 mu. That's it. Done. And this turns out to be, because the P final is E times, so you can just write as P mu square by 2 mu minus E square P mu square by 2 mu. And therefore we can write as P mu square by 2 mu 1 minus E square. So, okay, let me down here. So the final answer we can remember, or it's very easy to remember, is that delta K loss is always half mu into U relative whole square. That is the initial energy available, 1 minus E square. If you know the coefficient of restitution, you can directly tell me the loss which could have occurred in the CM flow. So now you need not to solve from the very basic, from the scratch. You know, if you know the E is what. So let's say for perfectly inelastic collision, where E is 0, all of the energy in the CM frame available gets lost. And for the obvious reason, because initially we had this energy and finally they will move together. So if the system will move together with same velocity, there is no energy in the CM frame. And therefore all of the energy in the CM frame get lost. And similarly for perfectly elastic collision, E is 1 and so delta K loss is 0, because we know that in perfectly elastic collision there is no loss at all. So the kinetic energy before and after, if you calculate, you will get the same answer. So this culminates one discussion of the collision. So we are done with the collision. Then what we'll do is something more about the Newton's laws of motion in the CM frame. So the next topic will be how to write the laws of motion in the CM frame. And probably this is the last page of my whiteboard. So we'll discuss in the next lecture. So now you can solve any question of collision or conservation of momentum. And the formula which we have derived today are the we can say the most powerful weapon to attack any problem and then get the answer in almost zero time. Now, in order to realize this all calculation, you need to derive and then spend some time with this calculation, and then probably you will be able to use it for the purpose of solving any challenging problem. Okay. So with that, I end today's lecture, and we'll meet in the next lecture with some more deep concept. And we are just two topics away. So one is the variable mass system, which is very important and useful. So we'll spend almost 1 to 2 lecture in the variable mass system, where we'll learn how rocket propels, how it moves. So we'll try to become the Elon Musk. And the last topic will be the calculation of center mass for continuous bodies. And the moment we end that topic, we'll go to the rotational dynamics. That is the biggest topic. And once we finish the rotational dynamics, then we can finish the rest in very short duration. So it will take maybe more than 2 months to finish the rotational dynamics. All right, guys. See you in the next lecture.
Okay, so